Hello, everyone. We are going to do a screencast right now on statistical power, what it is and how to calculate it. So hoping you can see this. And okay. So what power is all about is your probability of avoiding a type 2 error. You have, I'm sure, already learned in your statistics class about type 1 error, which is the controlled by alpha. The probability of making a type 1 error, as I said, it's directly of alpha, is the probability that you will go ahead and reject the null hypothesis when it's true. In other words, you will claim that the null hypothesis is not true when it actually is, or infer differences that are not real. And this is considered a major error, particularly in experimental design, where you're generally making strong causal claims because you're saying, in effect, that some kind of treatment causes a difference in means between an experimental group and a control group, when in fact it doesn't. Remember that your alpha rate means that you always have some chance rate that you're allowing effects may be due to chance within that 5%. And you're essentially stating that that is such an improbable area on the distribution that you are going to consider it negligible. But because you are allowing that type 1 error rate of 0.05, in fact, you could have so-called real results that represent a real change or real difference between one mean and the other, but that are outside the bounds of what you've considered chance. So that's type 1 error. The other that you may have heard less about is type 2 error, which is particularly more like historically been a concern in regression analyses. Both are really equally important, but typically experimentalists have worried about type 1 error. Type 2 error, which is represented by beta, is the probability that there actually will be some effect of an intervention, or there will be a relationship, true relationship, systematic relationship between two variables or constructs, but you will fail to reject the null hypothesis and therefore not be able to detect that. And so that's type 2 error. Power is 1 minus the type 2 error rate. So if you have, say, which used to be very common in studies, a type 2 error rate of 0.4 or 40%, your power is only 0.6, or you only have a 60% chance of detecting an effect when there is one. Now that is usually a function. The most common type of power error of the things that you can actually manipulate in your study that will cause you to have low power is sample size. And so it is considered admirable before you design a study to do a power analysis to determine what your target sample size should be to make sure that you have adequate power to detect effects if effects are there. So we are going to look at two power calculators, two general ways of testing before a study has been conducted or even designed, which is called a priori power analysis, or after the study has been completed, post hoc power analysis, which is kind of useful for a pilot study to see whether a lack of significant results may be related to the study was underpowered. And this is something also that can happen if you have little control over the number of your participants. So you might want to know, given an exact estimate of exact knowledge of how many participants you've had, what your obtained power is. And we're also going to look at 4 different types of analyses that you could do a power analysis for. Bear in mind, there are some more complex analyses where there are still disagreements about how to calculate power, and no really simple calculators for you available. So they're not as easy to do as what I'm going to show you, but I'm going to try to show you things that are certainly within your ken. So we're going to look at these 2 methods, one of which, the 2 types of calculators that I'm going to show you is, one of them is G-power. Make sure you can see that. So G-power is a long-standing and very reputable method for doing power analyses. I believe you have to download it. I've had mine on my systems for so long. I don't actually, I think it's a download. And it has many options. It has the t-tests, which are, you're all familiar. It also has chi-squared tests, with which you're familiar, z-tests, with which you're familiar, and f-tests, which you should be familiar by this point with analysis of variance. We're going to start by looking at t-tests. It also, by the way, has different types of power analysis. So as I said, there's a priori, compute the required sample size given alpha, which is usually set for you at 0.05. The power that you desire, how strong do you want your ability to detect an effect if an effect is there, and the effect size. The hardest one of these to come up with is the effect size, and I'll talk about that in a minute. It also has post hoc tests and a couple of other ways of thinking about power. Post hoc tests are computing the achieved power given alpha and the sample size that you actually got and the effect size that you actually got in your study. So it'll tell you, well, given that effect size and given those number of people, you wouldn't have overturned the null hypothesis because you only had a 50% power rate. So we're going to look at an a priori t-test of power and a comparison between 2 independent means. And we're going to do a two-tailed test because I have no idea what this, I don't even have variables for this power analysis. So I could hardly conjecture directionality. We're going to look at the effect size D. A cute little pop-up comes with conventions from Cohen. I believe that's 1988. My opinion of these conventions, pretty much like everybody's, is that the conventions or rules of thumb for the magnitude of effect size are poor, but we use them all the time. So and these are, Cohen's D is standard deviations of difference. So a medium effect size is a half a standard deviation difference in means between the 2 groups. Your alpha is more or less set. And so now you have to decide what you want your power, how high a probability of rejecting the null hypothesis if there is an effect do you want to have? How good a chance do you want to have of finding an effect if an effect is there. And the default here is 0.95. That's a very high-powered study. We're going to go ahead and run it, but it is considered, that's a high-powered study. That means that your power is the same as 1 minus your alpha. And it's not at all unusual for people to set power as less than alpha or less than 1 minus alpha, as I said, because type 2 error was not historically as much a concern as type 1 error. And I will leave that to your own judgment. For now, we're going to use the default. The allocation ratio N1 to N2 means are your sample sizes in your two groups equal? So we're saying, yes, it's a 1-to-1 ratio. So I just hit calculate, and it shows you the power area in your distribution, the alpha rate, and the extent of the difference between means and the critical t-statistic. The thing that we're most interested in here is the sample sizes. We've said 1-to-1, so the two sample sizes for each group are going to be the same, and the total sample size is 210. Now that's a lot of subjects. So we're going to just look at what would happen if we wanted less power. Actually, first, let's just look at what would happen if we felt we'd be content with having less power. As long as we didn't make a type 1 error, which we're controlling with alpha, then we figure we can always do the study again. Okay, there are a lot of assumptions I'm making here, but I just what I want to show you is that if you are willing to risk a less highly powered study, which means there'd be a chance that you wouldn't find an effect, even if the effect is there, you need fewer people. I think we went up to 210. And now we've managed to do without 50 people or so. And continuing like that, if you go down to 80, you need fewer people still to detect that effect. Also, a one-tailed hypothesis, you probably know, is stronger than a two-tailed hypothesis. So now you only need 50 in each group to achieve a power level of 0.80. And if you expect, based on your knowledge of the research and your theory about the strength of your treatment to be your effect size to be very large, you need very few people. So if you expect that your treatment group is going to differ from your control group by a full standard deviation at the end of treatment, then in fact you can get a not unreasonable power with a mere 28 people, and you can get a nice power of 90% with only 36 people. So that's how that works. I'm going to take another second and show you, wow, I hope I'm recording. I do hope I'm recording. Another site that I like to use sometimes if I'm on a computer where I don't happen to have the access to G-Power. And this is danielsoper.com. I know very little about Daniel Soper, but I do know that he has been a reliable source of power calculations for me for many years. So on Daniel Soper's free statistic calculators page, he has a sample size calculator. It's sample size calculator with Soper if you want a priori, the statistical power if you want post hoc. So we're going to look at a sample size power for student t-test. This is assuming you can choose, or you'll get both the results for a one-tailed and a two-tailed test. It is only for independent samples. we're going to do the same thing with, I believe the one I remember is a full standard deviation in Cohen's effect size, a 90% power estimate, and the traditional probability level. And you'll see that replicating the results from G-power, if you only have a one-tailed hypothesis, or if you have the strength of a one-tailed hypothesis, your sample size per group is 18. If you're looking for a more moderate effect size and you're willing to give up some power, you need 51 people or 64 people per group for a two-tailed test. And if you want the really highly powered thing that we started out with and a two-tailed test, you need 106 people per group. So this is just an exact replication. Every once in a while they'll have slightly glitchy differences in the two methods, but really they come up with the same results, and it's really your preference which method you use. Oh, I'm going to check. Yes, I am. Now we're going to go on to a couple of other power analyses in G-power. We're going to do a one-way ANOVA, and we're going to compare a priori to post hoc. So ANOVA is the F family of tests, and we're looking at an omnibus one-way test, rejecting the omnibus null hypothesis. Your post hoc tests for this would come under the t-tests. They'd be students' t's, independent samples, etc. And we are going to compute the required sample size. Now, the effect size here is measured as an F statistic, G-power, and I believe Daniel Soper also won an F. You know, where you get that F? Well, the conversion between F and the effect sizes that you will typically see in ANOVA output are not really worth our time. But because you probably have seen eta squared or possibly r squared, which also I think is given in SPSS output. But fortunately, G-power gives you this little pop-up that tells you, hey, you want a medium effect, put in 0.25. So we're going to put in, we want a medium effect size for the omnibus null hypothesis. Let's put in a power of 0.90. That's what I most typically do. And then you have to put in the number of groups. So that means that you have to know this is part of your design stage because it's prior to collecting your participants. It's helping you determine the number of participants you need to collect. And so you know how many groups you're comparing with a one-way ANOVA. So let's say that we're comparing 3 groups, treatment A, treatment B, and control. So the control is getting no prompt prior to taking a test, no anticipatory prompt. The treatment A is getting a anticipatory prompt in the form of a verbal cue, and treatment B is getting the verbal cue plus a graphic. I just made that up. So you've got 3 groups. And we're just going to go ahead and calculate the power. So our numerator degrees of freedom is J minus 1, where J is the number of groups. So that's 2. The denominator degrees of freedom is a function of the sample size, and the sample size is 207. So if you divide that by 3 to determine how many equal groups you would need, that's 67. Is 27 divisible by 3? Yeah, I think. Whatever. It's a lot of people in each group. 60, I'm sorry, I'm spacing out my basic numbers, but 60 something per group. So you need a lot of people to be in that. However, this is just useful for you to know. I'm not going to fiddle with the power rate and say, well, maybe I'm willing to sacrifice power. I'm not going to say, oh, I expect this gigantic effect of my treatment. I just expect that the treatment will be moderately useful, which is typical in social sciences, that we do not have overwhelming effects like you might see in the medical field. So I know now that I need about 207 people. You know, I put down in my target in a proposal something like 250, knowing that I'd have attrition, 225, knowing that I'd have attrition, so that when you get around to recruiting, you, for instance, know, well, I better not go ahead and trust these results because really the study was underpowered. I'd better get a better estimate by doing my recruitment for a few more months. We're going to look at the comparison of that with post hoc. So say that we knew that we in fact had achieved a effect size that was a little bit larger than medium, but we had only managed to recruit 60 people in each group. We hadn't met what our target was. We'd had fewer people. This will tell you what your actual obtained power is. And in this, with that sample size, you only had a 51% chance of rejecting the null hypothesis if the alternative hypothesis was true. Note that the effect size is not statistical significance. This means that you only had a 50-50 chance of overturning the null hypothesis, even with a fairly big effect. Effect size and statistical significance are not the same thing. You can have a pretty big effect and fail to overturn the null hypothesis, and that will tend to be because of effect size. Okay, I'm going to stay with G-power now so as to not to have to make too many transitions. And we're going to do a factorial ANOVA. Factorial ANOVA, you will not be getting to that in John's class. We will talk about it a little bit next, that'll be the 14th of May in our last class session. See what time it is because we actually have class pretty soon on my clock. And what factorial ANOVA is when you have more than one independent variable. So for instance, you are comparing Q before testing versus no Q before testing to multiple choice versus constructed response. Right? That's kind of a stupid study, but let's say that that's what you were doing. And there's ways of making, they're called, what are they called? STEM equivalent items, where your constructed response are the same in content, but they just lack the multiple choice. So you want to see whether it matters, whether people are having cues, and whether it matters differently according to the format that they're being tested in. That's not a very interesting problem posed, but it's just an example. So in here, you're looking at fixed effects, special, main effects, and interactions. And don't worry about all that language for now. Oh, we're still on post hoc, so we want to change back to a priori. We're going to continue to look for an overall effect size throughout the study of 0.25. We're going to go back to kind of I don't know why I prefer 0.90, but I do. And then the number of groups is the number of total cell sizes that you would have. So let's say that you had only no treatment B, just treatment, which was Q before testing versus no treatment. So that's two groups. And then the groups could also be configured, were also configured as constructed response or multiple choice. That's what we call a 2x2 design. And what it means is that you have four unique conditions. You have people who are getting Q multiple choice, Q constructed response, no Q multiple choice, and no Q constructed response. Four unique combinations. So that's four groups. And the way you calculate degrees of freedom for a factorial ANOVA is it's J1 minus 1, where J is the number of groups in one factor. So the factor where the choices, the groups are multiple choice and constructed response, has two groups. So J is 2, minus 1 is 1. And K minus 1, where K is the number of groups on the second factor, which is Q or no Q, two groups, 1. So our numerator degrees of freedom is actually only 1. And that's not very many degrees of freedom, by the way. And overall, we need a total sample size of 171. You'll notice perhaps that that's not divisible by 4. So if we want our groups to be equal, we might want to make it 180 or something. That would be divisible by 4. And so we need to bring 180 people in this to the study to have an probability of rejecting a null hypothesis if the alternative hypothesis is 2 of 90%. I'm going to do just one more thing of these because we are covering multiple regression. And so I'm going to look at the linear multiple regression R-squared deviation from 0. And in this case, it says, what's your effect size? The default is, this is an F-squared notes instead of F. So the Qs they give you for different effect sizes are different. And we want to overall of about 0.15, which is medium. We're going to put in my 0.90. So we're at F-test, linear multiple regression. The most important thing that you need to know about this, there are fixed and random effects where you're much more likely to be doing fixed effects in any kind of work you do. This is kind of beyond the scope of the class. And you're looking at R-squared deviation from 0, which means it's kind of like the null hypothesis is 0. And do you have a non-zero effect and its magnitude? And R-squared is a different effect size measure than F squared. And you can convert from one to another. And that's back to my cluelessness as to why most of the sample size calculators prefer to use F squared. So we're going to say that we have two predictors. To use someone's example from the class, we are predicting the number of professional development opportunities pursued over a 6-month period to psychological capital and grit. And so our predictors are 2, our dependent variable is the number of professional development activities pursued. And how many people do we need in that study? About 190 to achieve a power of 0.90. That's pretty much it. I will go back to the, let me go back to the screen. Not yet. back to the first screen and review that your alpha is managing your type 1 error rate. There is actually no name for 1 minus alpha, which would be your ability not to make, your probability of not making a type 1 error. We just talk about the type 1 error rate, which we usually set at 0.05, which gives you a 5% chance of rejecting the null hypothesis when the null hypothesis is actually the correct decision. Power is 1 minus your type 2 error rate. So if you have a 10% chance, beta, type 2 error rate, of failing to reject the null hypothesis, retaining the null hypothesis, when actually there is an effect and you should have rejected the null hypothesis. If you have, what did I say, a 20% chance of that, your power is 1 minus that rate, which is 0.80. And you want to minimize both of these error rates, and you can calculate this for most of the basic forms of tests, perhaps for all the basic forms of tests, but it's complicated for more complex analyses. And I hope that this was a helpful presentation. Good afternoon.